Hello all, welcome back to Code Hub. Today let us solve the lead codes weekly contest 328. This is the second problem of the contest and which is the increment submatrices by 1, and I think it is a quite decent problem, and let us solve this. You are given a positive integer n indicating that we initially have an n cross n zero indexed integer matrix filled with zeros, and we are also given a queries. It is going to be a 2D integer array, and there will be four variables which represents row 1 call 1, row 2 call 2, and for each and every query what we have to do is we want to fill this row 1 and call 1 denotes the starting cell of that submatrix, and row 2 call 2 denotes the ending cell of that submatrix. And for each query we want to fill the we want to increment the entire submatrix. So let us take the example 1. In example 1 the queries are 1 1 2 2, which is this is the 1 1 cell and this is the 2 2 cell, and we want to fill the entire submatrix. We want to increment this entire submatrix, and the result after this query execution will be like this: 0 0 0 0 1 1 0 1 1, and the next query which is nothing but 0 0 1 1. And with this query what happen is the starting cell is 0 0 and the ending cell is 1 comma 1, and we want to increment this matrix. It looks like this: it becomes 1 1 0 1 2 1 and 0 1 1, and we want to finally return the result of that sub after executing all the queries. So we want to do this, but it is very simple problem if we apply brute force. Brute force is nothing but we can just go for every queries, and we can just increment all the submatrix, and it will take an order of n square. Let us say at worst case it becomes order of n square, and for each and every query it may become order of m time. So the total time complexity will be order of m into n square, which will be nothing but cubic solution. And this, with this constraints, it is going to give us TLE, time limit exceeded. So can we optimize a little bit so that it gets accepted? Yes, we can do that. So each and every time we are actually incrementing the submatrix. So let us try to figure it out how we can do for a 1D array. Then we can try to modify this approach of 1D array to a 2D array. The problem for 1D array is nothing but if I'm given a 1D array of 0 0 0, and this is going to be the index 0 1 2 3 4 5, and if I give a query like fill increment the subarray which starts from the index 2 and it goes till the index 4. So if I give this as my query 1, and what happens, this is my query 1, and let us say we are having a query 2. What I'm saying is increment the submatrix from starting from 0 till 5. So this is my two queries. We want to do the same stuff in 1D array, and then we can just try to incorporate that approach to my 2D array. So what we can do is we will be trying to go for each and every subarray for in the queries, and we will increment it. But this is going to be an n square solution, right? For queries we can take m complexity, and for each query we want to run a loop of order of n, so it becomes order of m into n. So how can we reduce this time complexity? Yes, we can do this by Sweepline algorithm. Sweepline algorithm is nothing but it is a great algorithm for doing the reducing this time complexity. So what we can do is Sweepline algorithm is nothing but we will be incrementing the left pointer and we will be incrementing the right plus 1 point. We will be decrementing the right plus 1 pointer, and by doing that, after executing all the queries, if we have a running sum on that array, then we will get the required array that we need. So let us execute this first query by brute force solution. By brute force is nothing but while going through all the subarrays from 2 to 4, we will increment the index from 2 to 4. It becomes like this, and then after the second query it becomes like 1 1 2 2 2 1. So this is the array that we need after executing two queries, and this is by doing brute force. Let us do this by Sweepline algorithm. How can we do the sweepline algorithm is nothing but for each and every query we are having a left pointer and we are having a right pointer. Left is nothing but this 2 and this right is going to be 4 plus 1. If it is 5, 5 plus 1. If it is 3, it is going to be 3 plus 1. So what we are going to do is 4 plus 1, which is 5. R is 5. So array of L plus plus, for each and every query we are going to do array of L plus plus, and we are going to do array of R minus minus. This is what we are going to do. After doing this, what we will be doing is okay, let us execute these two queries in this input array. We are having 0 0 0 0 0 0 0 0, right? And we need another 0, right? 0 1 1 2 3 4 5. So let us since we are having one incremented pointer in R, let us have an array. Let us you can assume that we are having a array of 6 and it does not go to index out of boundary case. Let us assume that we are having some imaginary index of 6 as well, but our input array is another 0 to 5. Okay, now what we are doing is we are just doing this operation for each and every queries. So initially for query 1 it is going to be array of L, which is 2 plus plus, array of 2 plus plus, it becomes 1, and array of R is nothing but 5, so 5 minus minus, so it becomes minus 1. So after this query 1 it is going to be like this, and here we are not actually running a for loop at all. We are just decrementing the left pointer and incrementing the left pointer and then decrementing the right pointer. So let us do for the query 2 also. Query 2, it is nothing but 0, so we will be incrementing, and the right pointer is nothing but 5 plus 1, which is 6. We will just decrement it. So after executing all the queries, for this input we are having 2 queries. So after executing the 2 queries, the array will be looking like this. Now the sweepline algorithm is nothing but we will just do a running sum on this array. Running sum on the array doesn't mean if array of I is plus equals to array of I minus 1. So 1, then a 1, then a 2, then a 2, then a 2, then 2 minus 1, which is 1, then 1 minus 1, which is, but we don't need the last imaginary index, right? So we can just leave it. So as you can see that we by doing the sweepline algorithm we have arrived to the same solution that we did by brute force. So by brute force what we are doing is the time complexity will be order of m for the queries and multiplied by order of n for the subarray. Similarly for this sweepline algorithm, the time complexity will be order of m for the queries and order of n for the array finally while doing the running sum. So you can just see here the time complexity reduces to order of m plus n, and we have reduced one loop. So now if we can do this by 1D array, we can also do this by 2D array. How we can do this by 2D array? We know that for this 2D array we want to increment the submatrices, right? So to increment the submatrix, it is nothing but this is the starting cell 1 comma 1 and this is the ending cell 2 comma 2. So if it is like this, we can just consider this as each 1D array, right? For each and every row we can just consider it as a 1D array, and we can perform the same stuff by incrementing this left pointer and by decrementing this since it is out of boundaries, we can just decrement the right pointer. And similarly here for this third row we can just increment this left pointer and we can just decrement this right pointer. Consider in this while executing the query 2, while executing the query 2, this is the starting cell 0 comma 0 and this is the ending cell 1 comma 1. So for each and every row we are going to consider it as a 1D array, and we are going to do the same sweepline algorithm that we want to increment the left pointer and we want to decrement the right pointer, and we want to increment this left pointer and we want to decrement this right pointer. Once we have done this once we have done the executing these queries, what we will be doing is we can just traverse a whole matrix and we can do the running sum that we want to do in this sweepline algorithm. This is how we can just reduce the brute force of this problem. Brute force of this problem, how it will be is order of m for the queries and multiplied by the rows multiplied by the columns. let us say like this. So this is going to be a time limit exceeded. By Sweepline algorithm, how we reduce this solution? Yeah, order of m for queries, and that is it. It is going to be an order of m for queries, and plus we are going to traverse the whole matrix once again. So it is going to be order of r into c, row into columns. So by this we can just reduce the time complexity from cubic to quadratic. So this is how we can just solve this problem. Now let us hope you understand what I'm coming to say, and I have also given a dry run, so you can just quickly write in a notebook and just verify it how it is done. And this algorithm is a standard algorithm to solve like this problem. So what I have done here is I have the matrix. Since may get a out of boundary case, because the right pointer is incremented by 1, I have declared the size of this matrix to be n plus 1 and n plus 1 and initialize everything to be 0. And the same thing what we have done here, we have what is this? Just a minute. Yeah, what is this happening here actually? Sorry, this is order of m into n, m into rows, we can just say. This is going to be order of m into rows, because for each and every row we want to do, right? That's why it is not order of m. Okay, for each and every query, what we are doing is we are considering each and every row as a 1D array, and we are doing the same stuff, that incrementing the left pointer and decrementing the right pointer. So this is my start. This by query, q of 0 and q of 1 will be the start x and start y, and q of 2 and q of 3 will be my end x and end y. And for each and every rows, I am just having a loop here. For each and every row, r starts from start x and r goes till the end x and r plus plus. What I'm doing is I'm taking the left pointer. Left pointer is nothing but lx equals to r and ly is equals to sy, start y, right? So similarly, I am taking the rx and ry. Rx is nothing but the row, and the ry is nothing but that column plus 1, the as we see in the as we saw in the 1D array. So now we are just doing the step increment the left pointer, and here we just decrement the right pointer. So we have done this. Once we have executed all the queries, we want to do the running sum. How we can do? We can just traverse the matrix, and we can just say start from the index 1, and we can just say matrix of ij plus equals to matrix of ij minus 1. So once we have done this, we are having a matrix of size n plus 1, but we want to return a matrix of size n. So just I'm taking, I'm copying the matrix of ij to res of ij and having the size n. And this is how we can just solve this problem, and I will just submit the code as well. Yeah, it gets accepted. Hope you like the solution, and let me know in the comments. Let us see in the next lead codes problem, and until then, bye.